Guys, this is Mrs. Foy, and today we're going to talk about electron dot diagrams. So where we left off, you guys should already know how to write an electron configuration. Remember, that's kind of like the address of where the electron is. And you should also know how to write shorthand electron configurations. Sometimes those are called the noble gas abbreviated version because we use the noble gas before that element as the shortcut to be able to just write the valence shell electrons or the outermost energy electrons. So that's where we're starting off. So an electron dot, sometimes called a Lewis dot, because that is the scientist that made this. It's just showing you kind of a cartoon of just the outer shell electrons. Remember, these are the highest energy valence electrons. And these valence electrons are in the outermost orbitals, where these electrons are the highest energy. And we'll show you the pattern on the periodic table again. You should already have a pretty good idea of that. And these electrons are in the highest energy level. So they're important, remember, because they are the ones that are involved in bonding, right? So it's the outer shell electrons that are involved in bonding. So here's an electron configuration for oxygen: 1s2, 2s2, 2p4. And which of those electrons have the highest energy? And they're not all equal. We don't, as chemists, we're not interested in all these electrons. We just want the ones that are the highest energy. And we can see that they are this energy level, right? This energy level that's actually the row that those electrons are in. We can see they're in the second energy level. And so those two electrons that are in the s suborbital and the 4 electrons that are in the p suborbital are the ones that are the highest energy electrons. And so those are the valence electrons. They're going to be the ones that are involved in bonding. So these 2 and these 4 electrons are our valence shell electrons. All right, so here's germanium. So here's the whole electron configuration. And again, as far as a chemist is concerned, this is very nice to write out the whole electron configuration, but we only care about the highest energy electrons. And remember, these big numbers in the front are telling us the energy level that those electrons are in. And so what we are interested in here is we are just interested in the ones that have the highest number there. And you can see what that is, right? Those are the 4. Here is the 4th energy level here and the 4th energy level here. And so these 2 electrons that are in the p suborbital and these 2 electrons that are in the s suborbital, those are the ones that are the valence. Those are 4 electrons that are involved in bonding for germanium, not these 3d electrons that are 10. And so those 2 electrons in the 4s and the 2 electrons in the 4p are the valence electrons. And all those other ones that we see there are inner shell. They are lower down in the energy levels. And so they are not involved in bonding. Now, sometimes you'll learn, if you take AP Chem, and when you go to college and take chemistry, that sometimes that these electrons, for various reasons, will shift out of those patterns to a more stable pattern. But for our purposes right now, we can just look at the big number in the front, the coefficient, to tell us what the highest energy level is. So because, remember, when you write an electron configuration, the d energy levels are always lower, right? It's 1 energy level lower than the row that they're in. So can d orbital electrons ever be in the outer shell? No, they cannot. Can f orbital electrons ever be in an outer shell? They can't either, right? Because remember, the f orbitals that are down in the bottom, the 2 bottom rows of the periodic table, they can never be outer shell electrons because they are always 2 energy levels lower than the row that they're in. And so d and f orbitals are never going to be valence electrons. So remember the period, right? The period is the row. That's why it's called the periodic table. So these rows here, 1, 2, 3, 4, 5, 6, 7, Those are the periods or the energy level, or sometimes called the principal quantum number, which we give the letter N. Those are the energy levels. So the rho is the energy level. And we can see that the D's do not come into place until the fourth energy level. And then down in the sixth and seventh energy level, we have the F's, which are going to be 2 energy levels lower than the rho that they're in. And remember, the D's are always 1 energy level lower. So only the S and P electrons are ever going to be in an outer shell. And remember, what is the most famous number in electrons? It has to do with the number 8, right? So we call that an octet. A filled outer shell is always called an octet. And 8 is the magic number because that is the most stable electron configuration that an atom can have. And noble gases always have octets. And that is one of the reasons why they are relatively inert. That word inert means that they don't react. That is because they already have a full shell. Remember, the one exception to that is helium, and helium has a full outer shell at just 2 because in the first energy level, it can only hold 2 electrons. So 8, the full octet, 8 electrons, in the outer valence shell is what all the noble gases are going to have. So here we see the pattern, right? This is the beauty of the periodic table, is that we see a pattern over and over again. And so these guys in this column right here are always going to have 1 valence, right? Because of the way their valence electron, their electron configuration is written. These guys are always going to have 2. All the transition metals are going to have 2 because once we start those D suborbitals, they're going to be 1 energy level lower than the row that they're in. And so because they're 1 energy level lower, they can never be valence electrons. And so then we have boron's family is 3, carbon is 4, nitrogen's family is 5, 6 oxygen family, 7 the halogens, and then the noble gases have 8, right? So here we go. We're going to write the electron dot notation or the electron dot configuration, or sometimes called the Lewis dot configuration for sulfur. I can see that it's going to have 6 valence electrons. If I had a periodic table handy, I could look at the row and figure that out. I could look at the column and figure that out, right? So it's going to be those 3 S2s and the 3 P4s. Those 2 and those 4 make 6. And so the way I'm going to fill those out in a cartoon is I'm going to show 1, 2. Those are the paired electrons that I'm seeing right here. And then I'm going to fill in the other 4. I'm going to basically pretend like this is a box, an imaginary box, and I'm going to put in 3, 4, 5, and then the 6th valence electron is going to have to be doubled up on one side. It does not matter if you doubled them up here or here or here, right? It doesn't matter. So that's called an electron pair. And then these electrons here and these electrons here are called unpaired electrons. And that's going to help us make sense when we start to talk about bonding. Here's xenon, all right? Xenon has 8. I know that because it's a noble gas. So watch how I'm going to fill this. 1, 2, those are the S electrons in the that suborbital. And now I'm going to fill in the other 6. So I'm going to go 3, 4, 5. So I'm going to spread those out because remember, the electrons don't like to be together unless they're paired, unless they have to be paired together in the electron configuration. And then 6, 7, and 8, right? So that's going to have 6 dots. So that's it. Lewis dot, electron dot diagrams are easy, and I think you'll really like this. So at this point, I'd like you to finish the video. You're finished with this now, and I'd like you to do page 32 in your packet. All right, and I hope that's been helpful, and I will see you in class.